So I'm Anna. I'm an AI graduate student here. I work sort of on the intersection between AI, artificial intelligence, and cognitive science. And I'm co-advised by Tom Griffiths in psychology and Dan Klein here. So AI, big field. I'm just going to do my best to give you an overview of some of the main ideas and topics. Obviously, I can't cover all of it, but hopefully this will give you a sense of it. This up there, we have a robot bicyclist, which is kind of cool. And to get you thinking about some of the things we're going to talk about, with a robot, you have lots of things you need to do. You need to be able to figure out the motion, actually, for instance, grasping the handlebars, those feet. You also need to figure out images. When I see an image, it's just pixels on the screen. How do I figure out, for instance, whether it's a wall in front of me or just more pavement? With more advanced robots, you need things like speech recognition, ability to synthesize voices, et cetera. So we're going to talk about some of those challenges and also see a couple of videos. So it'll be a good time. So let you know, we're going to start off with just the definition of AI. I think there's lots of confusion about what AI is or isn't. So we'll give a characteristic of that. Some AI history. So AI started off, everybody was really excited, and then there was a long period of AI is never going to work, this is just not going to happen. And then it is revived, it's had lots of successes in recent years. So why did that occur? And there was sort of fundamental change in how people thought about AI. Then we'll get a tour of some of the cool areas of AI, and then step back to thinking about what does it mean for a computer to think? How should we characterize that? So this is John McCarthy, who sadly passed away last October. But he was one of the founders of AI at Stanford. And he said that AI is getting a computer to do things which, when done by people, are said to involve intelligence. So this ignores a lot of things like, well, if a computer does something intelligent, what does that mean? Do we have to change laws about what is a person, et cetera? It finesses all of that. It ignores things about consciousness, et cetera. But it gets at the core issue of, basically, we want computers to do things that seem sort of smart. And what do we characterize as smart? Well, when people do things. And so he's making that analogy between these things. And so when people started off thinking about how should we do AI, how should we make computers do things that are supposed to be intelligent, they started off small. They said, well, I don't know, I'm in the 1950s. My computer doesn't run that fast. I don't have that much processing power. Let's start on sort of a small, miniature world and see how well we can do there. And so this began, there's this big conference in 1956. Some really cool projects were presented, including with Alan Newell, a sort of pioneer in computer science, presented a logic prover. So probably high school geometry, you had some sort of sentence, like prove something about the angles when two lines intersect. And you had some axioms, and you had to go from those axioms to proving that statement. And so in 1956, they had something that could take things like that in actually logical sentences, but same idea, and automatically prove various theorems, and including some theorems that hadn't ever been proven before, so that people had failed to find a proof for, their theorem prover was able to find a proof for, which is really quite cool, because you don't think of 1956 computers as being able to do that. And so people were really optimistic about this symbolic reasoning and rules and symbols approach. So an approach where we have a limited set of things, and we have discrete ways of going from one to another. So there isn't a lot of uncertainty about what is this logical symbol, what logical sentence is entailed next. You have set rules for how you get from one thing to another. And this seemed promising. So another example was Shirtaloo by Terry Winograd. So this was, he had a computer, he had some blocks in this little mini world. It was just all on the screen, but the computer could manipulate the blocks on the screen. And it could actually work with natural language text. So with asterisk, sort of limited natural language text. But the person might type in, pick up a big red block, and the computer does it. Person says, grasp the pyramid. And you'll notice in this image, there are a couple of pyramids. So there's this green pyramid here, and this pink pyramid here. The computer says, I don't understand which pyramid you mean. So it figures out, like sort of a smart human might be, hey, I don't know what you're talking about. You need to give me more information. And it also could do things like figure out somewhat more complex natural language. So a person says, find a block which is taller than the one you're holding, and put it into the box. So it, you have to do a reference back to earlier in the sentence to figure that out. And that's actually, in bigger texts, figuring out what it refers to is actually a really hard problem much of the time. So they were like, hey, this computer can do it. It's working well in these small, limited rules and symbols worlds. This is going to work out for us. And so people were really, really optimistic. There was also some research about neural networks. So people said, hey, your brain is made up of lots of little individual neurons. They communicate to each other in relatively simple ways. Maybe that can be something we use for artificial intelligence. And so they had very simple neural networks, just a set of neurons that you give some input to. They do something, and then some neurons give some output, where neurons is a small little function on the computer. And again, they thought, hey, this is working pretty well. But both of these approaches ran into major difficulties, such that in the mid-70s, most funding for AI research got cut off. People said AI is never going to work out. Some people called the 1980s sort of the AI winter. Thought, and why did this happen? You might say, this seems to be working well. We just need to scale it up. So one thing to get you thinking about why that might not have worked out is, let's think about, all right, you have something, you want to program something that figures out whether something is a dog. So the first thing you might do is say, I need a rule that tells me whether, do all dogs meet this rule? One of the big problems that came up with the rules and symbols approach was when you're working with the real world, things get a lot messier. So you might say, well, all dogs have 4 legs. But let's say my dog has an accident, sadly loses a leg. It's still a dog, right? Or what if you only see part of the dog? You only see the dog's head, the rest of it's occluded. You still want to say it's a dog. And this problem arises all the time with the rules and symbols approach. When you're actually trying to deal with everything in the real world, it gets a lot more complicated. So one of the key ideas they had when AI came back, so AI started having success again, was to think about probabilities and uncertainty. So people brought in some statistics and some probability and said, this isn't going to be possible to define exactly this is that. We have one hard rule that separates everything. They said, well, rather than trying to specify a dog exactly, what's the probability that the image I'm looking at is a dog? So turning things into, let me figure out the most likely thing, rather than I have to have explicit rules, this or that. And so you might think about it in like speech recognition. The sound waves coming from my mouth, they don't sound exactly like some, really like anyone else when they say the exact same words. But a speech recognition system can figure out that the most likely sequence of words that I'm saying is some particular sequence. And that's been really key for making most AI systems work today. So one thing you might have seen, if any of you guys saw Watson play Jeopardy, I think that was last year. This is a computer program that played Jeopardy. And it was really neat that one of the things it did is it gave its confidence. So it had a confidence rating. If it was some cutoff threshold percent sure, then it would beep in, it would give an answer. So it had some idea how likely it was right, rather than just, I'm right, I'm not right, I can't produce an answer. There was another thing, so I figured neural networks probably should know a little bit, so I figured I would tell you the other thing that happened with that other strand of AI. So people also figured out some more math about neural networks. They figured out, hey, if we just have the circles there, we got circles, those circles, they stand for neurons. And they figured out if you don't have that intermediate layer, there are a lot of things you can't do. So your brain, turns out, isn't just one neuron talks to another, gives an output. There are layers of these things. And once you add in that extra layer, you can actually do some pretty amazing things. So one thing the post office wants, it has as well, but it wanted back before it had it, was a way to automatically read zip codes. So lots of zip codes and letters, you want to sort things quickly, so it needs an automatic way to read it. So this is a program that has a neural net. So it's basically a neural net has lots of little layers. The different rows different columns represent different layers. And it takes an input image like that, and you see the 5 isn't exactly perfect. It's got some spaces, but it's still able to recognize answer 145. So there's some people, actually neural nets are coming back into vogue in some ways in AI now. But I would say these ideas of inserting more numeric probabilities and mathematics into AI really helped it to surmount some of the problems with just having a small world, where it looked like things would be really good, but they didn't scale up well. So, all right, now you know a little bit of history of AI. Let's take a look at what we might want AI to do. So there are lots of things you might want AI to do. This is a little list from Wikipedia. So one thing is planning. So you want to figure out, if I have a goal, how do I actually accomplish that goal? I need to figure out what sequence of actions to take. I had to figure out how to get from my last class to here in Evans. And even though I knew where both of them were, I had to, for instance, couldn't just take a straight line. I had to find the doors. There's some planning involved. Learning, and in particular machine learning. So I think this is one of the most exciting parts, and we'll talk about it in a minute. But one of the other big things that helps with AI is if you don't have to program everything. It's really nice if you can just make the system figure out what to do. So we'll talk a little bit about some ways to do that. Natural language processing, understanding language and generating language. Things surrounding motion and manipulation. So at first you think, motion, that's not that hard. Then you start things like programming a robot, and it's bad if when it's trying to reach behind it, it stabs itself. That's a problem. So you have to, that requires both planning and thinking about how to move things. Perception, so if I get an array of pixels, I need to interpret that. So I recognize there are a bunch of people, there are seats, but how does a computer do that? And then creativity and general intelligence are things one might want to do that I'm not going to talk about. But you can think about them. OK, so as I'm touring these AI applications, you might think about how you would evaluate how well a machine performed at a task. So does it need to be perfect, or is it good enough if it's pretty good? So with the zip codes, you really want to have very high accuracy because there's tons and tons of mail being delivered each day. If even a small percentage of that you're sorting to the wrong place, you're going to have lots of delays. Might be that if I just want the system to try to detect a few events and I can then go through them by hand, maybe it's not so important that it be totally accurate. And then you could also be thinking about where you would draw the line between intelligent and non-intelligent behavior. And we're going to come back to that question at the end. So as I said, I adapted these slides from Dan Garcia, and I'm told that you may have seen this slide before. So this is about planning. So I mentioned one of the simplest applications of planning is the idea of getting from here to there. You see this in video games a lot. You have a non-player character, the computer controls. And if it doesn't have a very smart planner, it might, for instance, get stuck behind a wall. Let's say I'm trying to go here, and the video game character says, basically the algorithm might be, always go somewhere where you get closer to the goal. And that sounds sort of reasonable. I always try to get closer to where I'm going. But if I've got a corner here, I could get stuck here. Anywhere I go, I'm going to get farther. How do I get there? So that's, you might call that a low range of intelligence, sort of simple heuristics. You can do better than that. So there are algorithms that both take into account heuristic information, so they are guided by the idea that getting closer is better, but they look for a whole path. So they look for actually being able to get to the goal versus just in the next step getting closer. And that works pretty well. You've probably still seen some bad AIs in games, but hopefully they are getting better. And when done well, they actually can work quite well. There's also an idea of planning in terms of not just getting from here to there, but planning out, say, how hard should this game be? You want a game that's not too hard, but not too easy. So you don't want something that a novice player starts, can never get anywhere, they die immediately. That's no fun for anyone. But you also don't want an expert player comes in and they just beat it immediately. So one thing I was reading, as I was preparing for this lecture, I was reading about a tennis playing AI, where basically it figures out, watches how you play, and figures out how good you are, and then tries to plan out actions that will be of an optimal level of difficulty, where it thinks sometimes you'll succeed at hitting the ball back, sometimes you'll fail. And that's sort of a much more difficult problem, I would say, than just getting from here to there. But it is a cool problem to work on. OK, so I'm not actually going to talk much about games in this lecture, but they are a really neat area of research. So machine learning sounds like sort of a nebulous term. You can basically define it as a program learns if after an experience it performs better. Pretty simple. So if after something happens, it does better at some task, it changes the way it responds, then we can say it's learned in some way. So one easy application you probably all use every day is spam filtering. Even if you don't know you use it, university does some of it. And with spam filtering, the computer was trained. It saw lots of instances of emails that are spam, and lots of instances of emails that aren't spam. And it had to learn to make the right generalizations. So it couldn't learn, these are the only things in the world that are spam. That wouldn't be useful. What you want is for it to perform better now when it sees a new novel email it's never seen before. You want it to then perform better. And so that way of training a machine learning algorithm, where you give it this, these are examples of this, these are examples of this, figure it out, that's called supervised learning. And it basically produces a classifier. There are lots of different instances of this. So you might have seen, for instance, some object recognition things. So computer learns to pick out of images, these are where all the people are. So I think some people's cameras now even have this, where it'll put a little box around the face. And that's kind of cool. So that's an example where somebody said, here are all the faces, and it figures out what are the right features for that. An example that I'm interested in, any of you have seen Khan Academy, which basically teaches people things online. They watch videos. It's a pretty neat place. And they do different exercises. And for a while, they had said, well, the way we figure out whether people know this or they don't know it is if they get 10 in a row right, then we say that they're done, they've learned this topic, let's move on. But that's really frustrating if, say, you get 9 in a row right and then you make a typo. Like, no one wants that. So they wanted to do a better way. And so they realized we have lots of data. We have all these students doing practice problems, say some arithmetic problems. Let's just tell the computer which of these series the student got the next problem right, when they got the next problem wrong. And so it's, again, an instance of supervised learning. And it's now out there on the web being used. So machine learning sounds like, that's sort of complex. Maybe it doesn't get used. Maybe if it works, it's not actually AI. But this is actually, these things get used all the time. So it's one thing. Just because something works doesn't mean it's not AI. So the next way that you might think about a machine learning algorithm is an unsupervised one. So this is where I don't have a bunch of labeled data. I don't have these emails are spam, these are not. Instead, I have a bunch of data that I want the system to make sense of in some way. So maybe I want it to make clusters. So I might give it a bunch of images. Turns out my images all turn out to be trees and people. And it doesn't know that, but it might realize that, hey, trees tend to be green. All these images tend to have the same sorts of features. I'll make a cluster about those. These other images, cluster them over here. So it's finding some underlying structure in the data. And you can't necessarily say ahead of time what that structure is going to be, but it can be really useful for understanding big sets of data. For instance, I'm going to show you an example with understanding news in a little bit. OK, the last type of sort of category of machine learning is reinforcement learning. And this one is a little bit different in that you don't have all of your experience ahead of time. I don't give you a bunch of stuff. You learn, then I go deploy this thing in the real world. Instead, this, say, a robot learns in real time. So it figures out, I got a reward, something good happened to me. All right, I should adjust my behavior for that to happen more often. Or something bad happened, I fell off a cliff, I'll adjust my behavior so that doesn't happen. So going to pause momentarily here to show you a video of a robot actually doing some reinforcement learning. So the video I'm going to show you is a robot learning to walk. So this robot, all right, restarting, yeah. OK, so the robot has this little manipulator, and all it receives information about is just which way its wheels are going. And it gets sort of a plus, yay, when its wheels are going forward, and a negative when its wheels are going backward. And it doesn't know ahead of time that, for instance, this pushing backwards will make its wheels go forward. And so you see it sort of struggling, kind of working. Oh, we're going backwards. And so it's adjusting. And slowly, it's now doing a better job at going forward most of the time. So it's adjusting its behavior. And it's sort of learned, one thing you notice if you watch this video enough times, it's learned to kind of pick up its manipulator after each thing. So rather than before it was going like this, and it would send it backwards, now it's actually picking it up. But no one programmed that in. It learned that from its experience of getting positive and negative rewards. Yay. OK. So that was machine learning. The next two topics I'm going to talk about both involve machine learning, but they're applied in specific ways. So natural language processing is all about understanding what language means, understanding written text, speech recognition, and also generating language. So generating, say, a response. If I ask the computer a question, it has to both understand the language and figure out how to respond. This is sometimes known as an AI complete problem. So when I talk to you, you're drawing on your lots of experience. You know about things in the world. You know what makes sense. You know that cats eat fish makes sense. Televisions eat fish makes less sense. But that isn't really anything about the words, right? And one of the ways that we've been able to get around some of those issues is with statistical NLP, which is basically take lots of text, figure out information from it, compile it in some way, process it in some way, and use that to figure out what sorts of things make sense. So for instance, if you look at, so Google has provided lots of basically tables with probabilities of how often do these 3 words, these 4 words appear in a sequence, which means that, for instance, you can predict, if I type 3 words, you can predict the next word. So you've seen that when you do Google search, you type in, and it gives a suggestion of what it thinks you're going to type next. And the way it's able to do that is that it has access to so much corpus data, which is cool. So one thing you can actually figure out from that is that television hardly ever appears as the subject of the verb eats, cats relatively frequently, and so it can actually figure out one of those sentences is a good sentence, one of them is not, which is nice. So natural language processing is hard. Many people who've, at least until the last couple of years, had experience with something, dealing with one of these systems said, it's a pain. I try to get it to recognize my speech. I'm talking to my bank, and it can't understand what I'm saying. It's impossible. This is never going to work. But it's been getting better and better. And one thing that a lot of people, I think, have had good experiences with when I played with my friends, it seems to understand me, is the Siri thing. So Apple on their iPhone, they said, let's put out this assistant that does speech recognition. So it figures out what you're trying to say. And it takes actions based on that, what you say. So it might do a search looking for something. It might, as in this example, change my calendar about this appointment. So it actually does something, which indicates at least some level of understanding in the sense of being able to respond in an appropriate way to what you said. So that hopefully is making natural language processing a little bit less of just, that's a pain for me, in most people's minds. So I promised you an unsupervised learning example. This is one about natural language processing because in NLP, we oftentimes have lots and lots of text that we want to summarize in some easy way, or we want to understand what are people saying. So you have lots of news. How do you comprehend that? So this is something from the Stat News group here at Berkeley. What they did is they fed it a bunch of news documents, basically all the news documents from, I think, Wall Street Journal, Washington Post, a bunch of things, over a couple-month period. And they asked it to figure out basically how these articles varied. So what things tend to occur together, what words don't tend to occur together. And they told it what countries, what are different countries, and these are plotted by where they fall on these axes. So on the x-axis, you see on one hand we have first military growth leaders, and people are talking about those with particular sets of countries. They don't tend to talk about those words. They don't tend to say those words when they're talking about debt, crisis, Merkel, country, euro. So that was all the European debt crisis, and you see the European countries tend to cluster over there. When you're talking about those countries, these are the words that come up more. And it found these words automatically. So it wasn't that someone said, I think the European debt crisis is being talked about, let me put that in. Instead, it uncovers these are sort of the biggest variations that occur in the data set. So that's an example of something you might want from unsupervised learning. And and often interacts with HCI. So what is the best way to represent information so that people will understand it? OK, so robotics. I've alluded to this several times. I've never actually done research in robotics, but robots are really cool, and I think many people find them one of the most interesting parts of AI, or at least the most sort of viscerally exciting. So robotics brings together lots of different areas of AI. So it combines, if you have a robot that can understand language, it combines speech recognition, speech understanding, and speech synthesis, so being able to talk back. Does motion and planning, as I mentioned. Usually they need some sort of machine learning to be able to figure out how to move about in the world. It's actually pretty hard to program a robot to do exactly what you want it to do when moving, because there are lots of variations that occur. So I can't explain to you very well how I can walk, but I can do it pretty well. But it turns out I can't program very well how to walk. I can instead tell the computer, this is good, this is bad, and it learns from that. So let's see. So some examples here. Oh, machine vision. So I haven't talked much about machine vision. It's an area with lots of research, and it's a hard problem in the sense of, as I mentioned, you just get these pixels and you have to comprehend them. So that's another problem that robotics, for instance, on the top there we have this ping pong playing robot. So it has to figure out where's the ping pong ball, where's my opponent, where's my opponent's paddle. All of those things it has to be able to pick out of the image and respond to. There's an autonomous helicopter. So Peter Abiel, who's now a professor here at Stanford, or not at Stanford, I'm sorry. He was at Stanford when he did this work. He is now a professor here at Berkeley. Sorry. So one thing he did in his dissertation project was made a helicopter learn how to do tricks. So for instance, it can stay totally stationary up in the air, except that it's turning around. It can fly autonomously upside down, which is things that people hadn't been able to figure out how to do, people hadn't been able to program helicopters to do. But by using machine learning techniques, they were able to get a helicopter to do this. You know, it's very robust. It doesn't fall down half the time. It works. So in one project here at Berkeley, which I'll just show you a tiny clip of, is this automatic towel folding robot. So the towel folding robot, this is at 50 times speed, so it takes the robot a little while. But it's got this pile of towels, and it's trying to turn around. It's trying to figure out, where do I grab this? It's figured out, what is the towel like? How big is it? Restart. Nice little pile. So this towel, all right, it's got a different pattern. It has to figure out what's going on there. It's turning it around. OK. Oh, beautiful. And it saw where it put it before, so it made a pile of them. I'll let us fold one more thing, I think. So this is sort of a simple task that you can all probably fold towels. But it has to figure out all these little things that we sort of take for granted. Oh, and this one's different. So here, it's a washcloth now, so it's smaller. It has to figure out, how do I respond to that? Separate file for washcloths. We'll let it finish its towels. So, yeah, I think that's awesome. It's a very simple idea. And one thing various robotics projects have been getting into more is basically making robots that are helpful for things like folding towels. There are projects about making robots that can put away the dishes or put the dishes in the dishwasher. which can have some messy consequences if it goes badly, but it's pretty cool. OK, so that's my quick tour of some various areas of AI. To recap, these applications are tough. AI is having big successes, but it's also facing big problems, which makes it makes it something that's really fun to work on, because you're facing these really challenging ideas. So you have to know about context for lots of things. You have to know something about the world to be able to do well at these tasks. There's uncertainty about the input. You can't count on every time I see a towel, that towel looks exactly the same. And lots of these things require intensive computation. So one of the ways, for instance, we've gotten better at chess was computers got a lot faster, so we could plan ahead many more moves. That was great. So there, the underlying algorithms didn't maybe change as we got better so much as we were able to store more things. So AI is tough, but it's been relatively successful at making progress. And in cases like chess and checkers, it's perhaps better than people. So Deep Blue, the computer chess player, beat the world champion, grandmaster. So neat. OK, so Alan Turing thought about this question. He was this amazing computer scientist and mathematician, helped break the Enigma code, World War II. He defined a test in 1950 about whether a machine could think. And he said, OK, put a human in one room, put a computer in another room, and then have a third room where there's a judge. And the judge can communicate with the two rooms, either via typing or, in some cases, people thought about via voice. And basically, the judge can ask the things in the rooms whatever it wants, whatever he or she wants. I guess the judge is always a person. But the judge doesn't know which room has a computer and which room has a person. And Turing said, well, if the judge can't tell which is which, then we can say that machine has passed the Turing test. And in some cases, this was because of expediency. The question was, if you want to define something else, how do you justify, say, some other characteristic, requiring some other characteristic to say a machine is intelligent? If you want to be able to sometimes say that machines are intelligent, it's hard to justify, well, does it need to have neurons? Well, probably not. Does it need to think in some way that I can understand? I'm not sure. So his test was behavior. And in some ways mirrors the idea that McCarthy said later, the definition we start out with of it's intelligent if it does something that looks like what we think of people doing as intelligent. And so John Searle is a philosopher who's argued against this idea. And he said, all right, imagine you put someone in a room. They're locked in the room. They don't speak Chinese. They have a phrase book. In this book, there are Chinese characters. On each page, there are Chinese characters on the left side. And on the right side, there's some more Chinese characters. You tell the person, all right, if you see the Chinese characters on the left side, copy down the Chinese characters on the right side. And let's say now there's a slot where you can pass in a piece of paper and pass out a piece of paper. And the person manages to have a conversation in Chinese this way. So they get passed in Chinese characters. They use their phrase book. They copy things out. And Searle said, well, that's like the Turing test. And you would never say that that person understands Chinese. And so his argument is, well, this just isn't enough to say something about understanding. Understanding is something more complex. And that argument has gone back and forth. People have argued that, well, the person doesn't understand Chinese, but in some sense, the whole system understands Chinese. So just like there's not one neuron in my brain that understands English or knows about my dog, but as a whole, I know about those things. And so it's been a philosophical argument that sometimes in AI we like to just kind of ignore. But it's something to keep in mind that has set up this field and that people really do think about. OK, so in the last few minutes here, so in summary, AI systems excel in things that computers are good at. So games where there are set rules and where we can just try to look ahead lots of moves, computers are really good at those. Computers are good when they've got lots of data. So one of the big advances that has happened is just having the web to have tons and tons of data to be able to process. And that's made a huge difference. You can apply the same algorithms you were applying 40 years ago to lots of data, and they perform sort of almost as well as the best algorithms now do with very little data. So big data can help a lot. Constrained worlds they're good at. AI is getting better at language understanding and real-time robotics, so these sort of more complex, more human type things, making lots of strides. There are lots more applications I didn't have time to talk about. I'm happy to, I don't know if I'm going to have time for questions, but I'm happy to get questions afterwards, or you can email me. Couple plugs for classes. So CS 188 is one of the most popular classes on campus. It's AI. Dan Klein often teaches it. He's a great professor. You get a program Pac-Man to do intelligent things, which is really quite fun. So I encourage you to think about that. CogSci 131, Computational Models of Cognition, is sort of a more CogSci look at some of the same types of models. So it's also a fun time. So yeah, take a look at AI, and thanks so much for coming.